Very good evening, Janissa.
Good evening, sir.
Glad to see you. How do you do? How is preparation going on?
Uh, Physics, I didn't prepare yet, but I'm doing math and yeah.
Good, good. Mathematics, and then design, engineering, and also one more subject was there, no? English.
And physical education.
Ah, very glad that you are very enthusiastic, interested. Probably you haven't slept well. You feel a bit sleepy. Yeah, let's move forward. Uh, Yesterday there was some problem with my data, internet data. So there was no proper internet connection. So we could not continue with the second session of the lecture, Janice. We were at the point of discussing Le Chatelier's principle. And I told that Le Chatelier's principle deals with systems that are at equilibrium. And once the system at equilibrium is disturbed by the intervention of factors such as temperature, pressure, concentration, the system will adjust itself to a new equilibrium by counteracting the effect of the change or trying to nullify the effect of the change. As far as the effect of temperature is concerned on equilibrium systems, here we have a beautiful example given here. Uh, we do have two kinds of reactions based on the heat of the reaction, exothermic reactions wherein the heat is evolved. In such cases, uh, according to Le Chatelier's principle, lowering of temperature favors the reaction, whereas in endothermic systems, increase of temperature favors the system, favors the product formation. Likewise, pressure. Likewise, concentration. There are some beautiful examples to. Right. Yeah, there was some disturbance. Okay. Yesterday we were discussing about STP, standard temperature and pressure, and we have seen that the standard pressure, the 1 atmosphere is equal to 0.987 bar. Hmm? So such information may not be given in the question paper. So you should be prepared, Janissa, the value of pressure in bar because KH, the Henry's constant, is expressed in pressure units bar. And when you want to calculate the KH, you should know the pressure STP, okay, standard pressure. That we have seen. Coming back to Raoult's law deals with the very first colligative properties. We do have elevation of boiling point, depression in freezing point, and osmotic pressure. Those are the colligative properties. And as you can see here, uh, in this particular Raoult's law, we are dealing with solutions basically in liquid and solid in liquid. And if we consider two components that are in liquid form forming a solution, according to Raoult's law, similar to Henry's law. The pressure is proportional to concentration. The partial pressure of one of the components, for example, ethanol and benzene, or ethanol and water, if you say two component systems, the partial pressure of one of the components is proportional to its X always represents mole fraction. And the proportionality constant, if we put the proportionality constant P naught 1, where P naught 1 is the uh, partial pressure of uh, pure component. Uh, Here we have a solution of two components mixed together. For example, yourself and myself, forming a solution. Presume that I am ethanol and you are water. I am one component and you are other component. Okay, we are dealing with a solution made up of two components. You are one component and I am one component. Per se, I am ethanol and you are water. Okay, when we form a solution, above the liquid phase, there is always some components that are present in the form of vapor. That is what is called vapor pressure. The molecules in the vapor form above the liquid phase always exert a pressure, and that pressure is called vapor pressure. Ethanol in vapor phase exerts pressure, and water in also in vapor phase exerts pressure. So the vapor pressure of ethanol is proportional to the mole fraction of ethanol in solution. So P1 proportional to X1, where X1 is the mole fraction of one of the components, whereas P1 is the partial pressure of that particular component. And P1 is equal to, if we put the proportionality constant as P1 naught. Well, what is P1 naught? P1 naught is the partial pressure of pure component, like ethanol, absolute ethanol. Likewise, P2, it's your, as such, how do you behave? How do you talk? How do you walk? That is pure Janissa. Myself, pure in the nil. But when we are interacting together, our behavior changes, our attitude changes, our responses changes, and it is proportional to the relative amounts of component 1 and component 2. The partial pressure of ethanol is proportional to the X is mole fraction. Okay, mole fraction of ethanol. Likewise, if I say P2, P2 is proportional to X2, where the proportional constant here it will be P2 naught. P2 naught is the vapor pressure of pure component 2. We are only talking about binary solutions like Neil and Janissa together. Okay, we are forming a solution. Imagine I am ethanol, you are water. We are forming a solution. Okay, how much of myself am present here? How much of yourself are present in this solution? Depending on that, the vapor pressures also are proportionate to the amount of component 1 and the amount of component 2 that are present in the liquid phase. Okay, so according to Dalton's law of partial pressure, the total vapor pressure is an summation, an algebraic sum of vapor pressure of component A and vapor pressure of component B. So the total pressure exerted by the vapor phase components is given by P total is equal to P1 plus P2. And then substituting the values of P1 and P2 here, we have learned here that P1 is equal to P1 naught plus X1. Likewise, P2 is equal to P2 naught X2. We are putting X1, P1 naught plus X2, P naught 2 in the place of P1 and P2. And we know very well that the sum total of the mole fraction of A plus mole fraction of B in a binary solution, when they are summed up together, it should be equal to 1. Okay, so x1 can always be written as in terms of x2. x1 is equal to 1 minus x2. That is how this has come. Emma, you may have such questions, suddenly why x1 is replaced with 1 minus x2. Okay, even simple questions, you should not feel shy. Even an experienced teacher will have questions. You can always ask me any question that you come across, because you have to read word by word. Emma, it is time-taking process. It is energy-consuming process. It's not like a downhill process. Labyrinth. Labyrinth. Labyrinth means God bless. May God bless long life. Okay. Ah, in Hebrew, we say Labyrinth. Because at when someone has said me that the heart uh, you know uh, function stops for a fraction of second. Okay, hope you are able to hear me. Janissa, are you able to follow? Yeah, even small things, you should never feel shy. Even an experienced teacher like me or some experienced teachers will have always some sometimes even a familiar things we cannot recollect. Okay, we know very well in a two-component system, the sum total of mole fraction of A plus mole fraction of B together is 1. So x1 is simply written as 1 minus x2. Simple rearrangement will give P1 naught plus, okay, P2 naught minus P1 naught multiplied by x2. What does this mean? The total vapor pressure over the solution is proportional to one of the components that is present in the solution. X1, X2, mole fraction of component 1, mole fraction of component 2. So the total vapor pressure is proportional to one of the components, one of the two components in the solution. Okay, so P total PT is equal to P1 naught plus P2 naught minus P1 naught multiplied by X2. Okay, so what does this mean? Just by knowing one of the components amount, you can calculate the total vapor pressure. That is the beauty of Raoult's law. Using Raoult's law, you can calculate the molecular weight of solute and molecular weight of solvent, and many other practical applications are there. Okay, I will come to that a bit later. So when we have a mole fraction of component 2, of course these P1 naught and P2 naught are experimentally determined parameters sum up. We know the vapor pressure of pure ethanol, we know the vapor pressure of pure water. Okay, when we are forming a solution, the total vapor pressure, P total, is always proportional to one of the components mole fraction. It can be expressed in terms of x1 as well. Simply, you see, I wrote in terms of x1. x2 likewise can be written as 1 minus x1. When I put 1 minus x1, we can express pt in terms of x1 also. So the total partial pressure over the solution is proportional to either mole fraction of solute or solvent. Okay, I told you solute is the one component that is present in lower amount, and the solvent is another component that is present in large excess. That is how we differentiate between solute and solvent. Okay, ma? Ethanol and water, both are water only. But per se, if you have 5% ethanol, means 5 grams of ethanol in 100 grams of solution, means 95 grams of water and some 5 grams of ethanol. So ethanol here in this case is solute and water is solvent. That is how we differentiate between solute and solvent. So you have understood in simple terms, Raoult's law, the total vapor pressure over the solution is proportional to mole fraction of one of the components. Understand, Amma? So P total is equal to P01 into P2 naught minus P1 naught whole multiplied by X2. So you should know the mole fraction of one of the components to determine the total partial pressure. I will deal with one of the problems so that you can understand this in a better way. Okay. You can see this plot. This is a very beautiful plot, Janisa. It's only simply, y-axis is the vapor pressure, x-axis is the mole fraction. This again deals with solution. I told you the beautiful example. Now what is happening is sugar dissolved in water. Okay, that is solid in liquid. Here, it's not like sugar in water because sugar or salt, even though they are soluble in water, sugar is non-volatile. Salt is non-volatile. Here, we are dealing with systems in which both component 1 and component 2 are volatile. Okay, ethanol. Okay, acetone, benzene. These are all volatile liquids. Okay, ma? Uh, Chloroform. What is the formula for chloroform? CHCl3. Methylene chloride, CH2Cl. Okay. Even though you are practicing, even though you are studying, may not be able to recollect quickly, no problem. Okay. Let us try to go as fast as possible. You should never be disappointed, discouraged. Okay. उपवास का भोजन मीठा होता है. उपवास का भोजन मीठा होता है. माने when you fast and have your dinner late in the night, it's so sweet, after fasting, the meal becomes sweeter. Likewise, sweet are the uses of adversity. When you go through adversity, when you go through difficulty, the end result will be always sweet. Today, I'm a PhD holder. Today, I got the privilege of being in Israel for 6 years. Today, I got the privilege of gaining experience from Korea and China. Today, I'm really blessed to assist my aunt by, just sharing my knowledge with you. How is this possible? If I were not to come to IIT, if I were not to have a PhD, if I were not to have expertise in chemistry, I would have never got an opportunity to interact with Ushant, or I would never have got an opportunity to teach you. Okay, ma? So what I mean to say is today you are working hard. Tomorrow you will be in my place. You will be better than me. You will be serving many students. You may be teaching 500 students in one stretch, in one semester. That is the hope with which you have to read. Okay, ma? It is your exam. It is your exam. You should put all your effort possible. You should spend more time, refresh yourself, energize yourself, take often, some kind of, milk and nutritious food, have some fruits with you. Even when you are staying in hostel, try to have some bread, snacks, okay, some dry fruits. Dry fruits are, energy foods, okay. Such things you should always have in your room, mama, because in hostel it's not like being at home. At home, mother will take care of you, aunt will take care of you. In the school, it doesn't mean that nobody will take care, but in canteen you can have your food, you can have your drink. After that, you have to come back to your room, and then when you go on studying in the midnight, you may feel hungry. In the morning, you may feel hungry. So somehow, in the school there will be a provisional stores. You buy snacks, you buy fruits, put it in your hostel room. Okay, ma. So you need to replenish, energize to perform better. A sound mind in a sound body. Reading is not so easy, Janissa. Reading is the most hardest endeavor because reading requires concentration. Reading consumes much glucose levels in the brain. Okay, then what I mean to say is it's not a energetically favored process. It's not a downhill process. Okay, when water is pouring down from a hill, it is very easy for it to come spontaneously to the ground level because thermodynamically it is a very feasible process, and the free energy change is negative. Of course, in your class, in your syllabus, there is no thermodynamics that is being taught to you in this class. Probably you might have studied thermodynamics in 11th standard. But studying is an uphill process, Delta G is positive. It's not spontaneous. You need to apply more stress. You need to sacrifice something. Otherwise, it's not easy. Study or reading is the most toughest endeavor. Okay. It's related to brain. It's a cognitive effort. Okay. Okay. Let us come back to this plot. It's a beautiful plot. The y-axis is the partial pressure. Here you will see the okay. P naught 1 means the pure vapor pressure of pure component 1 per se is here. Vapor pressure of pure component 2 per se is here. For example, ethanol, benzene or ethanol water. Here in the x-axis, we have mole fraction. In the y-axis, we have vapor pressure. We have two y-axis. Okay. What is happening is when we vary the mole fraction of component 1, here the component 1 mole fraction is increasing. With increasing in mole fraction of component 1, what is happening is this way when we increase, you see, the partial pressure is also increasing. That's what we have studied. The partial pressure is proportional to mole fraction. Okay, when you increase the mole fraction in one direction for x1, okay, mole fraction is increased from 0 to 1. So you see the partial pressure is increasing for component 1 and you will reach a point to that extent when it becomes 1. Means this is the maximum partial pressure you can get, because at this stage you are having a pure component 1, ethanol. It has no other additive. Then likewise, in this way, x-axis from 0 to 1, the mole fraction is increased, and when you increase the mole fraction of component 2 from 0 to 1, you see a linear increase in vapor pressure of x2 is increased. This is the line 3 is the total vapor pressure. The total vapor pressure 2 either increases or decreases depending on the relative amounts of x1 and x2. So basically this figure deals with the mole fraction of component 1 and component 2 that is present in liquid phase. Okay, ma? Likewise, we can always express the mole fraction of component A, component B. For example, I'm component A, you are component B. I'm component 1, you are component 2. Because it's so simple, it's only two components. There is no other student, so I can only focus on you. Only teacher, student, two components. Only solute, solvent. Beautiful, no? Here, both two components are in liquid phase. What I mean to say is, forget about the solution for a moment. About the solution, what do you have? Some kind of vapor. And this vapor contains component A and component B. Okay. Both are together exerting some pressure on the solution. Okay. So, what is the partial pressure of component 1 and what is the partial pressure of component 2? Again, it is proportional to how much of, okay, component 1 and component 2 are present in the vapor phase. In solution phase, you are expressing the mole fraction of component 1 and component 2 as x1 and x2. Likewise, in the vapor phase, you cannot use the same terms x1 and x2 because the components that are present in solution phase amount is different than that is present in the vapor phase. So you have to use different designation. Okay. In vapor phase, it is called Y1 and Y2. Same person, me. Okay. If I'm in your presence, I'll be in excited state. Okay. I'm happy to see you. I'm happy to share my experience with you. I'm happy to teach. That is the excited state. This is my vapor phase composition. Okay. This is, okay. Like this is Y1. Then what is the partial pressure of component 1 in vapor phase? P1 is equal to how much of component 1 is present in vapor phase into total partial pressure. So P1 is equal to Y1 P total. P2 is equal to Y2 P total. If you do not understand anything, Amma, you can ask. Okay. Now let us see one simple problem. Okay, Janisa, here this problem is based on Raoult's law. Then we will solve some problems based on relative lowering of vapor pressure, elevation of boiling point, and osmotic pressure. I told you pressure proportional to concentration. Okay, ma? This is the key. In Henry's law, the pressure is proportional to concentration. In Raoult's law, the partial pressure is proportional to concentration. We can also express Raoult's law in some other way. I'll tell you. In this problem, let us see how we can solve this problem. We have here uh, two liquids. Okay, ma. One is dichloromethane, CH2Cl2, and another is chloroform. As you know, dichloromethane has a different vapor pressure than chloroform. For example, I am dichloromethane and you are chloroform. Okay, let us see. The vapor pressure of chloroform and dichloromethane at 298 Kelvin. Because the vapor pressure is always a temperature, a function of temperature. When you vary the temperature, the vapor pressures will obviously vary. So you have to specify the temperature is 298 Kelvin. And the vapor pressure of chloroform and the vapor pressure of dichloromethane are given 200 millimeters of Hg and 415 millimeters of Hg. You see, Amma, pressure is one particular parameter. It can be expressed in different parameters. It can be expressed in different units. Like we can express pressure in terms of millimeters of Hg. What's the relationship between millimeter of Hg and atmosphere? 760 millimeters of Hg is equal to 1 atmosphere. Likewise, 1 atmosphere is equal to 0.987 bar. Okay, we can express pressure in terms of pascals. Okay, so pressure conversion units, they should be always in your fingertips. They should always be recorded in your mind so that, problem solving becomes very easy. Every now and then, Nama, you have to put a notebook and you have to write down all these problems. Okay, when I discuss a problem today, you have to put it in the notebook and write down and see if you have followed all the steps. Like mathematics, chemistry too. We cannot say that, when you observe and you listen, it will be remembered in your mind. What we have to do is, like mathematics, we have to write down each step and ensure that we are clear with each step of the problem. Only then we'll be very, very clear about the understanding and reproduction of the problem. Okay, ma. So we have we have yeah, we have here two components. One is dichloromethane, other is chloroform. And yes, so we have two components, and the partial pressure of the vapor pressure of chloroform is 200 millimeters of Hg, and the vapor pressure of dichloromethane is 415 millimeters of Hg. We have to calculate the vapor pressure of the solution containing chloroform and dichloromethane, and the amount of dichloromethane and the amount of chloroform are given here. The temperature is 298 Kelvin. Okay, ma. So the question is how to calculate the vapor pressure of the solution. For this, what we have to do is, now that we know how much of chloroform is there, now that we know how much of dichloromethane is there, we have to first uh, recall the Raoult's law. Just now I told you, from Raoult's law, we know that the total pressure, okay, that's what we have seen. The vapor pressure of a solution can be expressed in terms of mole fraction of one of the components. It can be in terms of component 1, or it can be in terms of component 2. Okay, so vapor pressure of solution is equal to formula total pressure, total vapor pressure is equal to P naught 1 plus P naught 2 minus P naught 1 multiplied by X2. Okay, ma. We can express the total vapor pressure in terms of X2, mole fraction of component 2. Here, what is component 1? Chloroform is component 1. See, chloroform is component 1. Dichloromethane is component 2. And the vapor pressure of chloroform is 200 mm of Hg, and the vapor pressure of dichloromethane is 415 millimeters of Hg. So knowing the formula well, we have P1, P2, P1 naught, P2 naught we do have. What we have to calculate is basically X2. X2 is mole fraction of dichloromethane. If we have the mole fraction of dichloromethane, we can solve the problem using Raoult's law. Okay, now let us come back and see how we can calculate the mole fraction of dichloromethane. First, let us start with chloroform. What is the molecular weight of chloroform? You know very well how to calculate the molecular weight of chloroform. It is basically dependent on the number of atoms and atomic weight of each atom. Okay. CHCl3. The atomic weight of carbon is 12, hydrogen is 1, and Cl is 17. Okay. So, Cl atomic number is 17. Atomic weight is 35.5. So, chloroform 12 into 1 plus 1 into 1 plus 35.5 into 3 is equal to 119.5 gram per mole. That is the molecular weight of chloroform. Likewise, molecular weight of dichloromethane is 85 gram per mole. Likewise, sugar. If you take glucose, the molecular weight of glucose is 180 gram per mole. Likewise, water, 18 gram per mole. Sodium hydroxide, 40 gram per mole. Benzene, gold. Likewise, such things, it should be recorded in your mind. Okay, ma? From molecular weight, we can always calculate the number of moles of dichloromethane and number of moles of chloroform, provided we know the amount of dichloromethane and amount of chloroform. You see, the moles of chloroform is equal to, because the amount of chloroform is 25.5 grams. 25.5 divided by the molecular weight. Weight by molecular weight. 25.5 divided by 119.5 is equal to 0.213 moles. These are the number of moles of chloroform. Component A, X1. X1 is, no, N1. N1. N1 is number of moles of chloroform. Okay, then N2. N2, how will we calculate? N2 is equal to weight of dichloromethane by molecular weight of dichloromethane. 40 by 85 gram per mole is equal to 0.47 moles. Now, from moles, how to calculate the mole fraction of dichloromethane? X2 is equal to N2 divided by N1 plus N2 is equal to X2. Number of moles of X2 is 0.47 divided by 0.47 plus 0.213 is equal to 0.688. This is how we get the mole fraction of component 2. So we know the partial pressure, vapor pressure of component 1, that is chloroform. The vapor pressure of component 1 is 200 mm of Hg plus vapor pressure of component 2 is 415. Vapor pressure of component 1 is 200 multiplied by mole fraction of component 2. So we can easily do this calculation and we end up with a total pressure of 347.9 millimeters of Hg. This is how we calculate the total pressure over the solution, total vapor pressure. Then there is another part of the question that is related to mole fraction of each component in the vapor phase. Again, I told you, when you deal with components in the solution, the mole fraction is expressed in terms of x1 and x2. X is mole fraction of component 1 in solution. X2 mole fraction of component 2 in solution. Whereas in vapor phase, the mole fractions will be different. So they should be expressed in terms of another symbol, Y1. Y1 is the mole fraction of chloroform in the vapor phase. Y2 mole fraction of dichloromethane in the vapor phase. So we know very well that P1 is equal to Y1 into P total. The partial pressure of component 1, chloroform, in the vapor phase is equal to number of moles of chloroform multiplied by total pressure. Number of moles of number of moles of chloroform we already calculated, it is 0.312 multiplied by vapor pressure of chloroform gives the partial pressure of vapor pressure of chloroform in the vapor phase. Likewise, number of moles of dichloromethane in solution multiplied by vapor pressure of dichloromethane gives vapor pressure of dichloromethane. Once we have vapor pressure of chloroform and vapor pressure of dichloromethane, P1 and P2. Once you know P total, okay, we can always calculate Y1 and Y2. Y1 is simply P1 by PT. Y1 is equal to P1. P1 is vapor pressure of chloroform. It is 285.5 millimeters of Hg divided by total vapor pressure, that is 347.9. Likewise, number of moles of dichloromethane is equal to vapor pressure of dichloromethane, that is PCH2Cl2 divided by total vapor pressure of the solution. 285.5 divided by 347.9